this is Annapurnaske, and today we are here to predict the IPL match scores using machine learning. The goal here is to predict the final scores of an innings using past match data and real time info. Now, about the architecture and data flow, we start with data collection, then pre-process it to train the model and evaluate it. The flow is match data, feature engineering, model training, and then prediction, then evaluation. Next is about the dataset description. We used a Kaggle IPL dataset where the features includes the team's venue, current score, overs, wickets, batsman, bowler, and past runs. The data ranges from 2008 to 2023, and the next is data set. So here is the look of the data set. It includes all the key match details used to train the model. To sum up, this project shows how machine learning can help predict IPL scores using historical data. It can be useful for teams, fans, and analysts to understand match trends and make better decisions. In the future, we can improve accuracy by including more features like weather or player form. Thank you. And the further information will be given by Chandana.
Hello everyone, I am Chandana. Today I am here to explain about the model training testing. First, pre-processing steps. In this pre-processing steps, we handle the missing values, simplicity in a code which will be shared. And it's a common for a pre-processing step that we need to remove all the missing data for our model to perform well. Then encoding the categorical variables. This includes label encoding. This converts the string labels into the numerical values. Next comes a future scaling. Scaling the numerical features using min-max scaler as done in our uh, code, which we will show afterwards to normalize the data for a neural networks. Then we split the data into 80 and 20%. 80% of data is used for training for the model, and 20% of data is used for performance, which will be tested. Then comes a detail that is implementation. Here we are using Python programming language for our code. Then we use some of the libraries like Pandas, NumPy for data handling and numerical operations, and Matplotlib, Seaborn for visualization, Scikit-Learn for data preprocessing and matrices. Then here we are using Google Colab as an IDE. Then here are the steps followed. That is, first one is data cleaning and transformation, then feature selection, model building and evaluation and visualization. Then now let's move to the code. In the code, as in the first step, we are importing the libraries such as Pandas, NumPy, Matplotlib, Seaborn, and Skyline. Panda is used for data manipulation and analysis. NumPy is used for numerical operations. Matplotlib is used for plotting the graphs, and C1 are used for advanced statistical visualizations. Then here we are importing the function to split the data set into training and testing using Skyline model. Then importing the pre-processing, that is label encoder and min-max scaler. This converts the categorical variables into the numbers. Min-max scaler normalizes the future to range of 0 to 1. Then from Skyline metrics, we are importing a mean absolute error and mean squared error F2 score. Then accuracy, precision, and recall. These are all for the performance matrices for regression and classification evaluations. Then we are importing the keras and importing tensor flows. This is for building and training the deep learning models and machine learning models. Then importing the IP widgets as widgets from ipython.display import display clear output. This for creating an interactive widget in Google Colab, which we are using as an IDE. Then we are hiding the warning messages for clearer output. Then the step 2 is to load the data set. Here we are using IPL dataset of 2008 to 2016. The line here IPL is equal to pd.read. This particular line will read the IPL dataset from a CSV file into the dataset name called IPL. Then we are displaying the first five rows of dataset preview in it. Then comes the data pre-processing. Then here we are in a first line, that is df is equal to IPL dot drop. Here we are drop the unnecessary columns that are used in a model training. Then here x variable contains the input features and y variable contains the target variables. Then comes a label encoding. Here it creates a separate label encoder for a different categorical columns. Then applies the encoder to convert the string value into the numerical form for a better performance of the model. Then we are training and splitting the data, that is as we told here, we are using 70% of training data, that is x train and y train, and 30% of data for x test and y test. And we are selecting a random state 42 to ensure the reproducibility for a better accuracy and precision, not to overfit and underfit. Then feature scaling, as we told earlier, we are using a scalar that creates a max min scalar object for a normalization process. Then xtrain scaled fits the scalar to the training data and transform it to the range of 0 to 1. Then xtest scalar, this applies the same scaling to the test data without refitting. Then define and train model, that is step 4. Here we are using a that is we are defining a model keras.sequential that initializes a sequential model with input shapes equal to the number of features. Then first here we are using neural network algorithm. So it first hides the layer with the 512 neurons and relu as an activation function. Then second hidden layer with the 216 neurons, that is also again a relu activation function. Then in an output layer with one neuron, that is predicting a single continuous value, that is a total score target variable. Then it uses a Huber loss, that is which is robust to outliers instead of mean squared error. Then model.compile optimize Adam loser is equal to Uber lose. This compiles the model with Adam optimizer, that is adaptive learning and Uber loss function. Uses the test data for a validation, and verbose is equal to 0 disables the training log output. Then we are converting the training history to a data frame and plots the loss versus epochs. Here there are total 50 epochs. Then we are plotting that each epochs and losses, then grid, then we are showing that graph. Further will be continued by my teammate Kaustuba.
Hello everyone, I am Kaustuba and today I'm going to explain the model evolution. Now that we have trained our deep learning model to predict the final scores in the IPL match, it's time to evaluate how well it's actually performing. We use regression metrics first because our model is predicting a continuous number, the score. Uh, Regression metrics breakdown. Mean absolute error tells us the average absolute difference between our predicted and actual score. And if MA is 10, for example, that means our predictions are off by 10 runs or average. Mean squared error squares the error before our averaging gives more weight to the large errors. Useful to detect if the model is occasionally making very bad predictions. Root means squared error, just the square root of the MSC interrupted in the same unit as the target variables runs, making it more initiative. And R squared, this is the goodness of fit measure. It tells us how much variance in the target variable total runs our model is able to explain. A perfect model as an R square of 1, and we also visualize the training We also visualize the training and validation loss to check if our model is overfitting or underfitting. If the training loss is much lower than the validation loss overfitting, if both are high, it's underfitting. Ideally, they should converge closely. Even though it's a regression problem, we can also reframe it as a classification task just for interruptibility. We ask, can our model identify whether the final score will be high or greater than 180 runs? So we set the threshold of 180 and compute accuracy. How many times we were right, and precision of the predicted high scores, how many were actually high, and recall of all the actual high scores, how many did we catch, and F1 score, the harmonic mean of the precision and recall. This gives us the binary performance snapshot and particularly useful for commentary or tactical decision in the real matches. Let's moving on to the step 4, that is interactive prediction widget. Now to make things really exciting, we are added an interactive components using IP widget, and think of this as our mini IPL prediction app. How it works: we provide drop downs for the user to select venue and the batting team and the bowling team and striker or batsman and bowler. Each of these selection is labeled, encoded, or transferred into numbers because of the model only understand numeric inputs. And the code here, that is venue encoder dot transform venue widget dot value is one selections are made, and the user clicks predict score, and we gather the inputs and pre-process them, same scaling as training, run the models dot predict method, and output the predicted final scores instantly. And from uh, displaying venue widget and batting team widget, this makes the model interactive, user friendly, and more relatable to non-technical audience, and great for demos, cricket analysis, or just having fun during matches. And then we are moving on to the output, that is we have the graph of the model training and validation losses. The output shows how well our deep learning model predicts the final score in an IPL match based on input conditions like venue, teams, and batsman and bowler. The first loss graph, the graph shows the training loss and validation loss over 50 epochs. Both lines gradually go down, which means the model is learning over time, and there is no over 50 fitting since the training and validation losses are close. And second, the regression matrix. This matrix evaluate how close our predicted scores are to actual scores, and MAE is 19.41. On average, our prediction is off about 19 runs, and is MSC and RMSE. These also shows how much error we have, with RMSE being around 26 runs and R square is about 0.17. Only 17% of the variation in score is explained by the model, and this is quite low, so the model can be improved. And third, if we have classification style evaluation, we added it which by checking if the model can predict if the final score will be above 180, and the accuracy we got is 77%. The model is mostly right, and the precision is 77%. When it predicts a high score, it's right 77% of the time, and recall is about 14%, but it misses many of the actual high scores, and the F1 score is 23%. The balance between the precision and recall is weak. Interactive prediction, here the drop downs is shown. Drop downs at the bottom let the user select venue on team's batsman and bowler. On clicking the predict score, the model predicts the final score dynamically. Um, this whole output shows a working model, though it's still basic. It gives a decent prediction and a fun interactive way to test the match scenarios. And that's it for my part, and thank you. Further will be continued by Vinuta.
Matrix. This matrix acts as how will the model predicts a continuously numerical values. MA mean absolutely error 19.49 on average. The model prediction or about 19.49 runs away from the actual score. Lower is better. MSC mean square error 703.80. This is the average of the square differences between predicted and actually score. It penalizes larger error more heavily than MAE. Lower is better. Or MSC root mean square error 26.53. This is the square root of the MSC and is in the same units as the target variables runs. It is common metric for interpreting the magnitude of error. Lower is better. R square score 0.17. This indicates that the model explains only 17% of the variance in the IPL scores. This is reality is lower score suggestion the model does not fit the data very well. Higher is better, closer to 1. Classification style evaluation I score 180. This section evaluation the model ability to classify whether a match will have a higher score defined as greater than 180. Accuracy 0.76. The model correctly classifies whether a score will be high or not 76% of the time. Precision 0.67. When the model predicts a high score, it is correct 67% of the time. Recall 0.16. The model only identifies 16% of the actual high scoring matches. F1 score 0.2. This is the harmonic means of the precision and recalling, providing a balanced measure, measure of the model performance in identifying high scoring matches. A low F1 score indicates a poor balance between precision and recall. Next slide. Conclusion and future work. Conclusion. The project successfully predicts IPL score based on real-time matches condition using linear regression. Important note: while the conclusion states a successful prediction, the evaluate matrix on the previous slide suggestion that the prediction accuracy and ex- exclamatory power of the linear regression model are quite limited. Future work. This outlines potential improvements for the model. Try advanced model like try advanced model like random forest or XGBoost. These are these are more complex machine learning algorithms that can often capture non-linear relationship in the data better. Then linear regression include weather condition and pitch data. These are likely important factors that influence IPL score and could significantly improve predict accuracy.